Hello everyone, lecture for data warehouse. Today we are going to cover enhancing the performance of the data warehouse. In the previous lectures, when we were talking about different parts of a data warehouse, we were focused on how the data is organized within the data warehouse. We also talked about how the data can be presented in the form of OLAP cubes to the business layer, and we also talked about how data can be imported into the data warehouse through the ETL process. Now, once the data is available in the cube or available in the data warehouse, directly accessed by the data marts or by the business intelligence tools, we want to improve the performance of the data warehouse. Now, before we go into that performance part, because majority of the things that we are going to discuss in this class focuses on your knowledge about joins. Now, I know you have covered this probably in a bachelor's course or probably in an advanced database course as a review in your master's degree as well. But since this lecture depends heavily on it, so that you need to understand how it does it, so that's why I'm going to go over a brief overview of how joins are done. Now, typically, whenever you talk about joins means you have two tables and then you are trying to join them so that you can run a complex query on one or more relational tables. So let's say, for example, first of all, I'll explain it with a simple example and then I'll give you a realistic example. So let's say that I have a table which includes shirts, okay, and I have three shirts, which is yellow, green, and blue. And then I have another table which has all the pants, and the pants are red, green, and blue. My task is when I join them, I want to make sure that if a color is available in both of them, then I would like to join them. Now, inner join, whenever we tell inner join means that first it looks at the first table and sees that if there is a matching record in the other table. And if there is a matching record, then it will extract that record into the resultant table. So if suppose my join table has colored shirts and colored pants together. So currently, if you see yellow is not there in the pants, so yellow will be ignored. Second, I see that green is there, so green will be included both in the join table because green is both in the shirts and the pants. Similarly, blue is also available. So this is my final table. So you can see that it returns all the records from the left table if they have a matching record in the right table. And if there is records which do not match, then they are not included. If there are records which are not matched, then they are not included. So this is join, and this is a simple join that we have studied many times. Whenever we are working in an SQL query and we do not specify a join, by default, that is a join. Okay, that is an inner join. So if you specify it, your query may look like this. Select color shirts and color pants from shirt and join with pant table on. You have to specify a key because it will look for a matching value, right? It looks for a matching value. So you have to specify a key. Usually it is done by using the primary and the foreign key relationship. Other way to write this is similar to this. In the other way is select something from two tables where the ID of one table is equal to the ID of the other table. And this is how we usually write it. So this is whenever we write a query which is just plain saying from this table and this table where the IDs are equal, then we are actually performing an inner join. So this is what it means by an inner join. Let's take a realistic example as I told you before. I have two tables, which is student and a course, and I want to get a list of all the students and the courses they are taking from the program. So I will say I'll select the student name and student ID and the course name. If the student exists in both tables, for example, the student exists in the student table as well as the course table. That's why I have where STUID is equal to course student ID, which student ID in the course is actually a foreign key. So I will get a list of all the tables with a list of all the students who are in the student table and they are taking a course. So if a student is not taking a course, it will not be included. And if a course is not taken by any student, that will also be not included. So this is the basic concept of inner joins. Now let's talk about outer joins. There are three types of outer joins. When you talk about outer joins, we have left and right and full. So let's see one by one, what do they mean? So let's again go with the same example that we did before. We have a shirt table and we have a pants table. And we want to do, this time we would like to do a left join, a left outer join, or sometimes it's also referred to as the left join. So once we do left join means you just look at the tables where they are occurring. So a table on the left side is called the left table, and the table on the right side of the join is called the right table. So shirt is the left table and pant is the right table. So whenever you're doing left join, we pay more focus to the left table. So everything in the left table will be included, even if there is no match. Okay, even if there is no match, everything from the left table will be included. But if there is a match, you just put the match, and if there is no match, then you put null. So you do not ignore it. The only difference here is that yellow was here on the left side, but it is not there on the right side. Since I'm doing left join, I will include yellow, but since I don't have any matching part in the pant section, I will just put null. And similarly, I will go to the next one, which is green. Green has a match, so I don't have to do null. And blue has a match. Now you see, I stop over here. I do not include red because red is in the right table. And here I'm doing a left join. Okay, so in the left join, usually it returns every record in the left table. And I'm all matching records in the right table. But if there doesn't exist a matching record in the right table, then you use null. Okay. The way you write it is simple. You just say from shirt, and you specify, instead of just join, you say left outer join, and you specify the key on which you have to join them. Okay. And a realistic example, again, the same one that we did before. But if you do it this way, if you join it this way, if you use the left outer join, then you will get all students from, even if they are not registered. Let's say, for example, I am offering in my university, I have 10 students, example, 8 of them are registered for a course and 2 of them did not register any course. So, but if I do a left outer join, then I will get all the students, even if they are registered or not registered. So it will put them there, but it will, instead of putting a course name beside them, it will put it as null. Okay. The next one is a right outer join. When we talk about right outer join, we are focusing now on the right table. Up till now, we are focusing on the left table, right? So now we'll move our focus to the right table. So when we move on to the right table, here our main focus would be, we will have example, like for example, we will start with the same table. We have the shirts and the pants table, and then we would like to the right outer join. So we'll have the same color as shirt and pant as our join table. So here yellow will not be included because see, yellow is on the left table, and here I'm doing a right outer join. So if yellow doesn't have a match on the right side, I will not include it. So I will start with red first because I have to start the join from the right side. So first I will look for red. Is there any matching red on the shirt side? No. So I will just put null. And then I will start from green, and then I will put green, and then I will see blue, and then I will put blue. So yellow is not ignored because I'm not starting from the left table, I'm starting from the right table. So it returns every record from the right table and matching them with every record on the left table. So if there is a match, it will put the match. If there is no match, then you use null. So the way you use it is again the same way, but you just use a right outer join. So if I do this with my course example, I will get a list of all the courses and the students. But if suppose I have a course which no student is taking, I will also get that course here instead of ignoring it. So I will get the course. Even if no student registered for the course, I will still see it in my joined table. The last one is a full outer join. So in a full outer join, you are considering everything. Imagine you are considering for both sides, left and right together. So a full outer join means you are doing a left join and you are doing a right join. and you are removing the duplicates. So for example, yellow will be there, and then green, and then blue, and then you will go to the right hand side and say, okay, red, so I will put the red, and then green is already there, blue is already there, so I will just finish my join. So it will return all the records from both the sides. If they are not matched, then you get a null value. So this is how you write it, and in the example that we have been taking up till now with the students and courses, you will get a record of all the students and all the courses. So even if a student is not registered for the course, his name will be there. And if a student is, if a course doesn't have any student, the name of the course will also be there in the joined table. So I hope that is clear. So we have 4 types of joins. We have an inner join where we are only matching if a record exists in both the tables, if a matching record exists in both the tables. In the other example, we talked about the outer join, we talked about the left join and the right join. And the left join, we focus more on the left hand side table. Every record in the left should be there. And then in the right join, every record from the right table should be there. And in the full join, it's a mixture of both left and right. So all records in both left and right table should be included. If it's a match, you put the match. If there is no match, then you use null values. So now that we understand the basics behind the behind joins, we are going to use that in the explanation of various concepts that we are going to discuss today. Okay. One of the reasons why joins is important is because you remember that when we were making our star schema or snowflake schema, we had the fact table including all the numbers, all the numbers. But all the dimension tables are connected to the fact table by their surrogate keys, the SK values. So whenever you want to run a query and want to get more information, we have to perform a join. We have to join the dimension table with the fact table before we run a query. And joins can cause a lot of performance degradation. Because when you are trying to join things, the size of the join increases. And when you increase the size of the join, then you need space, you need processing power. So it causes a lot of issues. So you have to pay more focus on how you can improve the performance of the data warehouse by taking these factors into consideration. So the physical design of the data warehouse is very important, because usually whenever we are working with the data warehouse, the physical design of the data warehouse is very important, so that we want to design it such that the performance of query response is improved. There are 3 common techniques that are available to improve the performance of data warehouse systems. The first one is called materialized views. You may have heard about view, but in a data warehouse, we use a different kind of view called materialized view. It's nothing very fancy. It's just that that view, whatever view you are creating, is actually stored in the data warehouse. So you do not just create it and then remove it after you finish your query. You actually physically store it in your database so that future calculations can be faster. So this is called a materialized view, and we'll go into details about that. The second one is indexing. Now, indexing is something you have heard about a lot of times. Indexing is a technique that is used in OLTP systems to reduce the query response time. But usually the techniques that are used in OLTP systems cannot be used with data warehouses. So in this course, we will learn about those techniques which can be applied to data warehouses. And the last one we are going to focus on, which improves the performance, is called partitioning. Partitioning divides the contents of the tables into several files so that you can access them easily. You are increasing something called as parallelization. So when you partition information, you can execute your queries in parallel, increasing the performance of your data warehouse. So we are going to cover in this lecture only materialized views because there are some concepts which may need you to focus on. Indexing and partitioning, we will cover that in the next lecture. So let's start with what is materialized views. Now, before I go into materialized views, I would like you to understand, I'm not sure if you remember, again from your previous courses, what a view is. Now, view is an important structure that is created in a data warehouse. Views and indexes are two things that are created to improve the performance. Like, for example, in a normal database, I'm not talking about a data warehouse, I'm talking about a normal database. So in a normal database, when you create a view, the reason why people create a view is to improve the performance, so that you don't have to do joins later on. Okay, so that's why you do views, or you create indexes so that searching of a record becomes faster. So these are the two things that usually improve the performance in a database. So the same concept are coming over here. So we have, in this case, we have materialized views. So we have additional challenges, and we will see those challenges in a little while. So before we go into those, what is materialized views, and what are the challenges when we implement that concept in a data warehouse, we would like to first understand what a view is. Now, before we understand a view, let's go back a step back to understand what a schema is. Again, I repeated this. If you remember, I repeated what a schema is when I was telling you about data warehouse based schemas, which is relational modeling. So schema is typically the definition of the records in the database. For example, the schema can say a record will consist of the following. A record will may consist of a user ID, which is my primary key. It's a unique number. It may have a username, which is 40 characters, and then it may also have a date of birth, which is date. So this is the schema. Schema specifies what is included in my data warehouse. And then it also specifies like what is the data type, what is the size of the data that is included, and so on. So this is my data warehouse. This is the schema. So schema helps you know exactly what format to expect when you query the database. So schema usually helps you to know how to query the database, because if you know the structure of a table, then you know how to write your query. Every query starts with select something. If you don't know what is the database a table in a database structured like, you cannot write any query. So you should know how the table in the database looks like, so that you can write a query for it. So a database schema in general is defined as it includes the names of the tables, because we are talking about database schema, right? We're not talking about a schema of a table. Schema of a table will include the name of the table, the definition of the columns, and the data type, and the size of the columns. But in a database schema, it includes the name of the tables, the columns in those tables, the types of data in those columns will hold, and the relationships between the tables. Right? The relationships, if there is a foreign key or a primary key, foreign key relationship between the tables and the columns. So now, what is a database view? So view is a result of a query made to appear like a table. So imagine, let's say for example, I have a table, and in that table I have thousands and thousands of records. Now typically, I only run commonly. Let's say, for example, let me give you a realistic example. I have a database, and in that database, this is something that I do usually. So that's why I'm giving you this example. Now, I maintain a database of all the courses and all the faculty members who offer those courses in the college. The reason why I do this is because at the end of the semester, we ask the faculty to submit their course files. Syllabus, the documents, their the grades and everything that is required for the course, we ask them to submit it. And this is done every semester. So now currently I have been here for around 6-7 years, and for all those 7 years I have asked faculty members to submit that information, and that information is recorded in the database. Now usually whenever the university asks me to do a report, I do it only for a semester. I don't do it for the previous 7 years, because the reports are semester by semester. So I usually access every semester more frequently than the whole table. So my whole table probably currently includes around 5,000 records. But for a semester, I only am concerned with, let's say, there are around 300 sections offered per semester. So instead of 5,000, I want to only focus on those 300. So whenever I run a query, if I don't use a view, what will happen? It will always run the query on the 5,000 records. So whenever you run, say select this from this table where this equal to this. So my query usually looks like this: select star from the course table where semester is equals to 1442-1 or 1442-2. So I'm restricting the search, but the database doesn't know that, right? It did not create an index. So what it does, it will run the query. It will first find me a smaller table. It will create a smaller table, and that is called a view. Now you can create it yourself instead of asking the database to do it for you. So when you create a view, then all other future queries can be done to the view rather than the complete database. So let's say I have this table and I run a query, say select A, B, C from table C, from table, whatever table is that, where C is greater than 3. So in the first one, I'm restricting the number of columns. You see, I'm selecting only A, B, C. You can see clearly that there are 4 columns. So in the result, the number of columns will be 3 now. And also the number of rows will be reduced because I'm using a conditional statement where C is greater than 3. So I will not get all the rows. So I will get a smaller part, smaller cube of the bigger table that is in my database. So the result of running an operation on a table, if it looks like a table, smaller table, this is called a view. This can be saved as a view. It's not called a view, it's a result. But you can save it as a view so that in future, you don't need to run a query on the bigger table. You can run it on the view to save time. Because in a view, the number of records will be smaller and it is focused because you are only focusing on C is greater than equal to 3. So views usually allow you to execute complex queries, complex select statements, and then save them into a nice looking table. Okay? A properly designed view allows skilled developers to optimize a specific query for others to use. So if a view is very intelligently done, then other people will only use the view rather than using the whole table. So you make sure that whenever you create a view, you create it based on the demands, based on the needs of your business intelligence reporting softwares. So views can restrict certain information from user groups. Views can also be used. Like for example, I have a table with many information, but I don't want everyone to see that. So what I do, I create a smaller view and give people access to the view rather than the whole table. Okay, so that's why it is a view. And if it is poor, if it is not done properly, then your view will not be correct, right? Your view will not be correct. It will result in poor performance. So let's take an example of a view, which I just showed you, but let's understand it. So let's say we have 2 tables, and then when I execute a query, it will create this view. So it will take some records from the table A and it will do some records from the table B, and this will become my view. So in the previous example I was giving you, I was taking only one table, select A, B, C from one table, but here I'm taking more than one table. So views are more popular when you do it with joins, because now you are going through 2 information. Let's say for example I have a table of 5,000 records, as I told you before, and I have another table which is related to this table and it has 3,000 records. You know, if I run a query, how many records does the computer has to see? 5,000 into 3,000, which is very high, right? Which is very high. So that's why whenever you are doing something, you do a join. So when you do a join, you are restricting the number of items, and then you run a query on that joined view. And that is what you see over here in front of you. We have 2 tables, and when we run a query, we create an intermediate join between table A and table B, and we create this nice looking table which we can save it as a view. So in future I can only run my queries to the smaller table rather than going to the big table which has all the information, when sometimes I don't need all the information. I'm only focused on some part of the information. So here is an example of creating a view. So we say create view honor student. So I'm creating a table, a list of all the honor students. So as, and then you usually have a bracket and say select a student ID and student name from table A, from student A, from table name student. And then I'm selecting the GPA and the graduation year from the table B. And then where I'm first joining them, which is the inner join. As you can see, I'm using inner join. Student A ID is equal to the B student ID. So I'm just joining them based on the primary and foreign key. And I'm restricting them now by saying B.GPA is greater than 4.5, because honor students are those students whose GPA is more than 4.5. So this is how you create a view. Now when a view is created, you can now in future, for example, if you want to find out how many honor students are from CS department, or how many honor students are from IS department. So now you don't have to go to your original tables. You can only look at the view. Okay. Yeah, I know that I did not save the department, but suppose that in the view you already have a department. So if you have the department, then you don't have to go back. You don't have to go to the original tables. Just remember this terminology. Whenever you're working with joins, the original tables are called, or whenever you're working not with joins, but with views, the original tables, the table A and table B in this picture, are called base tables, base relations or base tables. So view is the view table, and the original tables that the view is constructed from is called the base tables. So now, as I told you, the main focus here is what is a materialized view. Because we want to focus on materialized views, right? So what is the difference? First of all, I give you an example of a view, right? So what is the difference between a view and a materialized view? But let's first understand what is a materialized view, and then I will tell you the difference between both of them. So let's say, for example, a materialized view is a view that is physically stored in the database. So a view that you saw previously, it's only constructed when you create it in a session, and then it is just in the memory. It's in the memory. It's not stored on the database. It's not stored physically on the database. The database only has tables. So views are created, but they are not saved. So once you, for example, you restart your database, your view is gone because it was there in the memory until you used it. And then once you refresh or clear your cookies or you restart your session, your views are gone. So a materialized view is a view, it's also a view, but it is physically stored on your database. Materialized views enhances the performance. So how does it enhance the performance? It pre-calculates the operations and stores them, and stores the results in the database. So if you already have those calculations, you do them, you save them as a view, and then in future, people can query the view rather than querying the original data warehouse, because the original data warehouse will be huge, right? So you create something called as summary tables. These summary tables are called views. They are used to eliminate the overhead, because you don't want to do joins again and again. If you do joins again, it is very expensive. Okay, so that's why you try to reduce the joins by pre-computing. The main idea here is pre-computing your join. So you decide that I'm going to probably run this query probably later on many times. So I'm going to do it once. I'm going to save it as a view, save it in the database, so that in the future, whenever I want to run a query, I will just go to the view and then run it. That's it. But since you are actually storing it, because previously, in the normal system, the views are stored, and then once you restart your system or refresh it, your views are gone, right? So you're not wasting your space. You're not storing them on the database. But when you are doing it with materialized views, you are actually saving that view in the database. So in that case, you may be wasting a lot of space. Whenever you are working with distributed systems, multiple systems connected over the internet, then you can also use views to replicate data. You can create a view and then you can copy this view into different systems so that people may run queries faster in a distributed system. Okay, and then you can use some sort of mechanism to ensure that all these views are the same. They are not contradicting. Because this is one of the main focus. One of the main focus is to make sure that all the views that are generated from the main table are correct. If they're not correct, then that means there is a big issue. And we will see that this is one of the issues that you have to understand of how to do it. And this is the main focus of the class today, is how we can make all these views consistent. Okay. So just to give you an example, the basic difference between a normalized view and a normal view and a materialized view is that a normal view, whenever you query the table, the base table, you create a virtual table, this virtual view, which is not inside, which is not stored physically on your database. So it is only executed when you execute a query, when you execute a view statement, and then it is gone. That's it. And then you don't save it. You don't save it in your database. It's in the memory of your database management system. Whereas a materialized view is one where the query gets to run and the data is saved in an actual table. So you create a smaller table and then you save that table physically in the database like a normal table, so that later on you can actually refer to it and execute queries on that view. It is not lost. Okay, so the data in the materialized view gets refreshed when you tell it to. So usually the materialized view, it's a smaller copy of the base table, right? So you need to tell it like now refresh it, because main table changes the data. Someone makes an update query or a delete query or an add query, the main table changes. So how are you going to update the materialized view? You have to tell it. Because see, in a normal view, you will delete the view. So you will not need to make sure that they are consistent or not, because you create it for a smaller purpose. You execute your query, which is faster, and then you delete it. You remove the view. That's it. So you don't have to worry about making them consistent. But if you're working with materialized view, since you're storing that view in the database, you have to make sure that whenever a change happens in the base table, that change is reflected into your materialized view. Okay, so this is very, very important. Now there are some issues that we have to discuss, and this is what we are going to talk about in this class. So do you think, as I told you just now, do you think anything wrong with the materialized views? I already gave you the answer in the previous one, which is the first problem, which is I need to make them consistent, right? I need to make sure all the views are consistent. That's the first major issue that happens. So whenever there is an update to the normal base table, we need to make sure that that update is propagated to the materialized view. This concept is called as view maintenance. Okay, it makes sense, view maintenance. Your view is created once, but once you're in operation, you have to make sure that the view is updated. Otherwise, people running the queries on the views will get incorrect answers, and we don't want that. So that's why you have to execute view maintenance. Another issue here is the number of aggregates that you want to calculate in a data warehouse usually increases exponentially. So it's not possible to create all possible aggregates. You cannot create summary tables for all possible values. You remember I told you aggregates can be monthly values or weekly values or quarterly values. Now there are many types of aggregates, daily, monthly, and you can do it by city, by province, by country. So there are many possible aggregates, but you cannot do all of them. You cannot create views for all of them. So because views are saved in the database, and you cannot afford to waste, because the number of records in a data warehouse is in billions. You cannot afford to create views for every small aggregate. So that's why you have to select the most important one. So selecting which materialized view to create is also a problem and a research area in performance enhancement using views in data warehouse. The third one is whenever we have created a view, the queries that you make to the data warehouse needs to be rewritten, because you don't want to access the data warehouse or the database directly now. You have to go through the view. So if some information is available from the view, you have to get it from the view. And then if it is not available from the view, then only you go to the main data warehouse. So you have to rewrite your queries. So these queries will improve your response time. So you have to rewrite them. And this is one of the third problems. And the final problem is also that you cannot anticipate what kind of queries people will ask. So you will not sure. Like for example, this is related to selection of materialized views, like which views to create. Which views to create is based on what type of queries people will ask. And it is all based on guess. There is no science behind it. Some companies may like reports quarterly. Some companies may like reports monthly. So you cannot anticipate what kind of queries people are going to ask. Or sometimes a company says, yeah, I'm going to do quarterly reports. And then they will come back at the end of in the middle of the year and say, no, we decided that quarterly is too late, so we want to do it monthly. So it becomes a headache, so you have to do it again. So it is not a science, it is not something fixed, it is just based on your anticipation of how things will happen. Okay. So as I told you, the first issue that we are going to focus really on is the maintenance, is view maintenance. We want to make sure that we are able to maintain the views, the data in the views, if something changes in the main base tables. So as I mentioned before, the process of maintaining, the process of updating the information in the materialized view, whenever there is a change in the base relation, is called view maintenance. Now there is incremental view maintenance, where whenever something changes, you do it incrementally. Do not want to create the view again. You're going to waste a lot of time again. You have to delete the view and do it again. So that's why one of the preferred methods in data warehouse is to do incremental maintenance. Incremental maintenance means you just compute the changes and then you store and then you join the changes with the actual view. Okay. So this changes, you will see later on that these are called delta tables. Delta tables. I'll write them somewhere. I'll probably fix this slide so that incremental view maintenance, you compute changes to the view. These changes are actually stored inside a table. It's not an actual table, it's a shadow table. So you just create that one, and then whenever that table is created, these tables are called delta tables, and these tables will be merged with the view, so that this is the way to update a view incrementally. I think I may have skipped something. I should have written it, but please make a note if you are watching this. Just please make a note that view maintenance can be. There are two ways view maintenance can be done. It can be done in a I don't know what, there is no term for it, but it could be something like it is done completely or incrementally. Completely means you delete the view and create a new view. Any update happens, you create a new view and delete the old view. Now you can see the problem with this. It is easy to see the problem. It's very time consuming. Every time there is an update, a small update, if there is a read, if there is a write, if there is an update, is a delete. Every time there is an update, you are going to delete the view and create a new one. And you never know how many views you have in your data warehouse. So doing all of them will slow down the performance of your data warehouse. So you don't want to do that. So that is complete maintenance. So the other way, that usually preferred way of doing maintenance in a data warehouse, is using incremental view maintenance. When you do incremental view maintenance, you calculate the changes only. You say, okay, if a change happens, say you keep a record of the change. They say a new record is added or a record is deleted. So you keep a record of those changes, and then from those records, you create a smaller table of the record changes table, which is called a delta table. Delta table can be for addition, can be for subtraction. So addition means you are adding a new record, subtraction means you are removing a new record. Now remember, we don't do updating. Updating doesn't happen. So updating means you are actually adding a new and removing the old. So this is update. So this is just a basic thing. Just remember that. So whenever you do this, whenever you perform this operation, so the view, you incrementally record it into a smaller table and you call it as a delta table. And that delta table is then merged with your view. So this delta table is merged with your original view, and then once it is merged, then your final table will be the complete one. And you do this every time there is a change to the base table. So every time there is a change to the base table, the view is updated. This is called incremental maintenance. Okay. Now the view maintenance problem can be analyzed usually in 4 dimensions. The first dimension is the information. It refers to the information that is available for view maintenance. What kind of information you are going to use for maintenance? Is it keys? Is it constraints? Is it the whole base table? So we will see that there are 2 major ways, and we are going to focus on the 2 ways and the operations. The second one is the operations, a type of operations that can be handled: addition, deletion, or updation. As I told you, updates we will consider them as a combination of addition and deletion. So we'll not consider updates separately. So we'll study only two operations, which is update, which is add and delete. And the language which is used to define the view, mostly it is SQL, right? Because we are focusing on the SQL databases. And then finally, it is instance. Instance refers to whether the algorithm works for every instance or for a subset of the database. Subset of the database means sometimes you whatever operation, whatever algorithm you are using for view maintenance may not work for the complete database. It may work only for subset of the database, which is not our case. We are not going to focus more because this is a very highly available research area. So these are the 4 dimensions usually people consider it whenever they are discussing the various algorithms or approaches to view maintenance. We are going to focus on the first 2 because the third one is constant. We are using SQL. As I told you, there are others, which is MDDB, MDX, data queries on cubes, but we will focus on SQL because we have been using SQL for the all the previous things that we did in this course. So we will focus on SQL. The 2 things that we will keep on repeating is what information. Based on the information, that is like there are 2 types of algorithms, and then for each algorithm we will study 2 operations, which is addition and deletion. So view maintenance typically, without the details, it looks like this. Suppose you have a sales table. A sales table has 3 columns, which is product key, customer key, and the quantity, which is our fact table. Remember, a sales is a fact table. And then suppose we want to create a view from this fact table, and that view we call it. We have to name a view because we are storing that view in the database. So let's say we name the view top products. So we have to define what should it contain, right? So let's say, for example, usually whenever you define a view, you define using these symbols. Even if you don't remember the symbols, don't worry. I'm not going to ask you to remember the symbols. It's just to understand what the view is about. Okay. So if it's a pie product SK, that means create a view. Pie means having all of them, all the records. So all the records, all the product keys, all the product SK from the sales table. I will specify sales table later on, and then I only want those keys, those product keys, where the quantity of that sales is more than 150 by the customer. So if I have a customer who has made more than 150 orders of a product, not one customer, any customer, but more than 150 items of that product has been ordered by customers, then this will be my top product. So I want to create a view which satisfies this criteria, this criteria. So I want to keep a track of all the products for which at least one customer, so it can be more than one customer as well, but the total quantity should be how much? 150. That's why I'm using sigma. The sign that is, you see the circle sign is actually a sigma. Sigma means the sum of the quantity is greater than 150 from the sales table. Okay. So there, as I told you, there are 2 cases we are going to look at. The first case is insertion. How does insertion happen in a materialized view? So we already created the view, right? So let's say, for example, this is my sales table. This is my base table. This is the base table. I am going to add a new record to my base table. That would be, let's say, P3, C3, and 110. So I'm adding a new product called P3. I'm not adding a new product because the sales table is a fact table, right? So let's say, for example, a customer C3 purchased a product P3, and the quantity that he purchased was 110. So I want to add this to my sales table. Add a new record to my sales table. So if you look at it, I'm not going to change anything. I'm not going to change anything in my top product, because you see the product that is being added, it says only 110, right? So 110 is less than 150. So I'm not going to add it. I'm not going to change anything in my view. My view remains the same. But let's say I do the same thing, but this time I'm going to add a new record, and the record here is P3, C3, and 160. Now 160 is more than 150. So that now once this condition is satisfied, now I have to go and modify the view. So that this product, that new product P3 has to be added to the top product view. Okay, so this is the case of using insertion. When you're doing insertion, you have to check whether the coming value, that is the added value, is actually satisfying the constraint, the condition for the view. And if it is satisfying the condition, I have to add it. If it doesn't satisfy the condition, then I don't have to add it. Okay. The other maintenance that I told you about is deletion. The case 2 is what is the effect on the materialized view when I delete a record. So whenever I'm deleting a record, let's say for example I have a sales table, and this time I'm going to remove a customer 3, which already purchased C3, and he purchased 160 items. Okay, so what do I have to do? Do I have to change something? You can see that, for example, I cannot delete P3. I cannot delete P3 now, because you know that product P3 can be purchased by someone else. P3, I'm removing customer 3 who purchased P3, right? Maybe customer 2, there is another customer who purchased 200 quantity. So based on this, just this information, I cannot remove it. I cannot remove it directly. So I have to go back to the sales table and search the whole sales table and find out if there is another customer who purchased P3 which was more than 150. If it is there, then I cannot touch the product table. If there is no customer, then I can remove it. So just to understand that deletion, whenever you want to delete something, it needs additional information. I have to go and check the sales table. Okay, so this is the basics. This is the basic on which we are going to discuss the next 2 algorithms. Okay, this is the basics on which we are going to discuss the 2 major algorithms for maintenance of views. I hope that is clear. Okay. So as I told you, view maintenance, there are 2 main classes of algorithms used for view maintenance. The first one that uses full information. Full information here means it uses information from the base tables as base tables. You remember in the previous one, I cannot delete a record from the view unless and until I have to check the base table. So whenever I have to do this, this is called this algorithm is using full information, and it is very bad because you have to go back and you have to search the base table. Whenever you are trying to maintain the view, you should not go and touch the base table. Otherwise, there is no reason, there is no benefit of creating the view, right? There is no benefit of creating the view. So we try to avoid it as much as possible. So there are some algorithms which are trying to improve the performance by doing something, and we are going to learn that today. The other type of algorithm is called partial algorithms that use partial information. So in partial information, they don't go to the base table. They just use the information from the view itself and information from the things that were added or removed, whatever. It never goes to the base tables. Okay, so it never goes to the base table. So these are the 2 basic type of operations that are involved for view maintenance. You either do it by full information. That means you have to go and get more information from the base table. As you saw earlier when I gave you an example of the delete operation. The delete operation, I cannot perform the delete operation unless and until I have to go to the base table, base sales table, and check whether is there any other customer who bought product 3. And I have to check the quantity of that purchase. If it was more than 150, then I cannot delete P3. But if it was less than 150, then I can delete P3. Okay, so this is full information. But there are cases where you don't need to go back to the customer table, or not the customer table, I mean the base table. So this type of algorithms which do not go back to the base table are called as partial information. The algorithms that use partial information. So we are going to study the insert and update operations on both the algorithms, some using partial information and the ones using full information. And we're going to do that one by one. So before we start with the maintenance of full information, let's take a quick break, and then we will in the next video I will start with the view maintenance. So view maintenance will cover both full information and the one with partial information.